All right. Yeah, so first things first, this is not going to be a sell of Databricks. It's just going to be an open discussion on open source tooling and the nature of LLMs. So hopefully this is open and accessible to everyone. And a quick show of hands over here. How many people have used a large language model before or played around with it? Okay. How many people work with machine learning? Okay, a few people. All right, so let's start from the beginning. What I want to do in this talk really is to go over how LLMs have changed the normal machine learning life cycle that we are all very familiar with, and then what this actually means in terms of the challenges that we face as developers, training models or developing applications. Then I'll walk through some of the new improvements in MLflow to handle these latest changes. And for each of these, there will be a code demo, and you can also download the code after this. There are actually going to be 3 hands-on demos, so hopefully this is a good variety for people. So LLMs have changed the machine learning life cycle. If we go through the normal cycle that we're all familiar with, you start with your raw data, you might ingest it into your cloud storage, then you do feature engineering. A lot of attention thus far also has been focused on training. So models like XGBoost, you do a lot of hyperparameter tuning on it. You compare your logistic regression model with your XGBoost, and then after that, you might deploy the model to a container or even to a VM. So how this changes with LLM ops is firstly on the raw data level, you are working mostly with unstructured data at the moment. So you're going from tables to text documents or images. When we talk about data prep right now, a lot of this usually means putting your data into a vector index. So how many people don't know what a vector index is? Okay, so how many people do know? Oh, okay, a fair few. Yeah, so for people who may not know, a vector index basically is a way to store your documents so that you can retrieve it very easily, and you can do what's called a semantic search. So if you ask a question, you can match that question semantically to a document that matches that question. So that is the advantage of a vector database. So we use a lot of that with large language models, which we did before, but not as much. Then when we move into the training, what is very new is that we are no longer usually trying to update the weights of the model itself. So traditionally with something like logistic regression, you are retraining the model to learn parameter weights. But usually with large language models, it's just way too costly to fine tune the weights. Even if you use a pre-trained model, you need at least A100 or A10 GPU, which is very compute intensive. Not many people actually want to do that. So we do what is called prompt engineering. And the idea behind prompt engineering is because these models have such good language understanding capabilities that you can kind of guide the model to the output you want based on how you ask the question. So if you say, answer the question, what is Spark? Then that may actually give you a better answer than if you just say, what is Spark? Because you're giving it an instruction, answer the question. So it's this way of guiding the model without actually updating the weights that is predominantly what we do right now to get the results we want. Then when we talk about deployment, we do have a step where you want to query your vector database, usually for source documents or more information to give to the model. And then after that, also, you may just call a third-party API to give you back your response rather than calling the model itself, which is very, very large and very expensive to host. So all of this is an overview of how we've seen large language models change machine learning, but we can actually dive deeper into each of these sections, which is what I'm going to do right now. So if we talk about data prep, as we mentioned before, typically we're dealing with a lot of unstructured data, but even more than that, the domain of inputs that we get is a lot larger because you are giving people license to literally ask anything they want. So whereas previously you may only be able to say to a model, predict the price of an HDB. Right now you can actually ask the model, what is the average price in Yishun over the past 5 years, and then give it a table. And ChatGPT can actually answer that question for you. So the range of inputs that you get is much larger than previously. And so to handle this also, how you ground the model by giving it informative information, for example, any SOP documents that your company might have, is equally important right now. And then so consequently, there are multiple right answers because when you ask a free-form question, like summarize this article, there are many different ways of summarizing an article that are equally valid. So it's not the case anymore that you can compare the model's output to a set of responses that you can then calculate the error or look at the differences between the labels. We're dealing with something that is a lot more nuanced here. And so then we don't have labels for this. So this is one example. If you ask a question, how do I use Apache Spark to compute the mean value of a data frame column? Then there are different ways of answering this question that would actually work for you. Okay. Yep. So then when we talk about vector, when we talk about the steps that we go through, this is the typical application. So if you ask, why did the driver stop, right? So who knows how Spark works? If you know how Spark works, there is this concept of a master node that orchestrates your compute that is called the driver. But if you are not familiar with Spark, what do you think a driver is? A driver is someone who's driving a car. So if you ask an LLM, why did the driver stop? Ideally, if you want to get the answer you want, you would need to supply more information to the model. And in this case, we can include documents like the Spark documentation to the model. And then you say, okay, based on this documentation, answer my question. So then the large language model can then give some suggestions. Oh, maybe it was an out of memory error, or one of the workers failed, and then garbage collection, So that's how we can actually ground the model to return answers that we want. And right now, there's really a proliferation of so many different vector indexes in the space. The basic idea around handling a document index is you have your documents and you might use an open source model or one of the proprietary ones like OpenAI. And then what you do is that you create a vector representation of these documents to store inside your index. So this is just some sample code using the Llama index, which is an open source document index. Or in this case here, we're calling OpenAI embeddings as well, and then putting it into a different open source database, which is Chroma. Yeah. Then when we query, we put this in, and then we embed. When we ask a question to the large language model, we include both the question itself as well as the documents that we've retrieved from the database that will help to answer this question. So that is what has changed on the data prep side. And then when we talk about training, firstly, it's less data intensive actually, even though these models are very, very large and then they took like days or weeks to train. When we actually use them as an end user, you actually need less data than, say, if you were training your own BERT model. So the idea is that you can, if you want to do fine tuning, you can actually get significant performance improvements even with low data volume. So maybe 500 documents. You fine tune the model for one epoch, and that can actually help make the model more contextual to your domain, whether it's law or medicine with different jargon. And if you do just prompt engineering, like different ways of asking questions to the model, you don't actually need additional training data. But the inference logic actually changes a lot because there are different ways of querying the vector database, and the shorter, you actually get shorter iteration cycles, because when you're trying to figure out the best way of asking a question to the model, you can rapidly cycle through different prompting templates and different parameters very quickly, much more quickly than, say, if you have to wait 1 hour to retrain the model and then look at the output, wait another hour after you change something for the model to finish training. And lastly, also, there's a greater emphasis on human in the loop evaluation. So because now evaluation, we can't really compare it to a golden set of labels. If we're talking about question and answering or summarization, which is what these models are really good at, we still rely on humans to give appropriate evaluation of how well the model is doing. So this is what we do. This is an example of prompt engineering where we start off with one template, like answer the following question about Apache Spark, or you can also say be concise if the model starts to become too long-winded or it starts to repeat itself a lot. You can just tell it be concise. And to me personally, this blows my mind because there's a degree of steerability is something that we just didn't have before. And then the third way, you might also try asking, okay, be concise and also include references to the Spark documentation to support your answer. So immediately here you can see, how do we begin to keep track of everything, and how do we begin to compare the responses to these three prompts in a systematic way, apart from like trying to recall what we asked the model before or using an Excel sheet. And then on top of that, you may even try different models. So different ways of asking the question, and then you may also be trying OpenAI, which is proprietary, or if your institution has data privacy concerns, you may then be looking at self-hosting your own open source model like MPT. So then the parameters that you have to keep track of starts to change, starts to become a lot to manage. And this is one example of how you would do prompt engineering with the open source tool LangChain. So what LangChain does, it does allow you to insert your prompt into this prompt template class. So the nice thing is then you can put in different parameters so that you parameterize your prompt, and then you put that into your chain where you can then switch in and out different models, which is quite nice. So how have we evolved to begin to handle these changes to the machine learning lifecycle? So firstly, we talk about evaluation. How do we do better evaluation when we're so much more reliant on humans in the loop? So we do have a new evaluate API that was released in MLflow 2.4. This is an example of the code where you load the data using a new log data function. And then for evaluate, you include the model type. In this case, this is text summarization, and the target that you want. In this case, because it's summarization, some data sets do come with a reference or a gold summary, even though that's not the definitive answer. And then you can call MLflow either to evaluate based on established summarization metrics like perplexity, or you can just compare the example side by side. So if you remember previously, we needed to keep track of the different models, the different parameters. So all of this will appear here inside the UI. So how does this actually look? If you have a notebook, and this can be a Jupyter notebook as well, if we pip install our MLflow, then the first thing you want to do is to load your data set and then save it as an MLflow data object so that we can actually keep track of this. Then after that, if you've used Hugging Face before, or if you haven't, Hugging Face really is right now the de facto model repository for these large language models. Anything that's coming out from Facebook or Google usually will be hosted on Hugging Face as soon as possible. So they do have a pipeline, and what we're going to do here is to call this pipeline using their standard API, and we say we want the T5 model here. And if people need zooming in, we call the T5 model and then we give it some text to summarize. So all of this here is the standard Hugging Face code. And what we will do after this is to start an MLflow run, log the actual data, and we can set the context here, whether it's training data or text data, and then we log the model so that we register it as a transformer model. And after we log the model, we get a unique URI that references the model. So when we want to call evaluate, you can call this URI, pass it your test data set, and then say this is a text summarization task. So for this one, you can compare the output side by side, and you can also compare established metrics like the Rouge score. So eventually, when we want to view the experiment, you will see something like this, where I'm comparing a T5 model with a BART model side by side. And if I go to the Evaluate tab, then you can see the two models over here, and I can actually compare the output with each other. So from this, it looks like they're both quite comparable to each other. So this is how we kind of get around the idea that you do need a human in the loop to evaluate all this. What's coming up in future releases is to actually have a prompt UI. So you can then go back in and then try a new prompt interactively without having to re-engineer your code. So this is what we mean by how evaluation has changed. And when we talk about, say, we've evaluated our model now, we want to package it, then MLflow traditionally has had what we call a model format. And so what this means is that you have a standardized way of deploying your models using MLflow, despite the fact that your model may have been trained by any of these many different libraries, or your deployment environment may be also very varied, from edge deployments to batch to streaming. What MLflow does is that you can save it into this generic format, whether it's just with Python or scikit-learn or TensorFlow, so that your downstream applications can actually use this model without having to rely on what the upstream tools were being used. So again, to handle this new proliferation of large language models, there has been an introduction of what we call the transformers flavor. So transformers are a specific architecture of large language models, and because of this, they do have certain aspects to the architecture that you want to log. So things like the way that you split your unstructured data up, and the kind of pipeline that you're using, whether it's conversational or question and answering, and also the kind of inputs and outputs that it expects. So what the new MLflow transformers flavor does is that it distills all this information down into metadata that you can keep track of. And better than that also, I think now with the proliferation of fairness and bias that people are interested in, when models get published onto Hugging Face, you see that they do also include a model card, which includes information on what this model is good at, what it's not good at, the data that it was trained on, So people are a lot more upfront about what the model can and cannot do, so that you don't just use it for a purpose that may not be ethical or may not be suitable. So what the transformers flavor does is that it will pull the model card from Hugging Face if there is one available, and it will also log that model card into the model metadata. So what we're really aiming for here is to have a standardized interface for all these different transformer models, and there are so many, from llama to alpaca to red pajama to dolly. So it's really nice to have a standard interface to be able to log these models. And then ultimately, what is the real kicker here, I feel, is it also unifies inference. So when you're trying to deploy this model, you don't have to use a different format for each type of open source model. As long as it's hosted on Hugging Face, it's part of their transformers library, you can actually use this flavor and then deploy your model using the MLflow API. So what does this look like in code? We actually, the good news is it's not that difficult. If we have our Hugging Face API, again, this is standard Hugging Face code over here, we want to initialize what we call a pipeline. So the pipeline takes care of your tokenization and then the actual running of the model itself. Over here, we say we want the task to be translating English to French. And our model here is our T5 small, which was released from Google. And our tokenizer also is the T5 model. So we initialize this pipeline from Hugging Face, and then we create what's called a signature. So a signature is an expectation of what the model's inputs and outputs is. And we will store this signature inside the model metadata as well. And after we run our experiment, again, like before, you can see there's all the relevant metadata of the model that is logged for us over here, including the inputs and outputs. So when we log this translation pipeline, we use MLflow and then transformers.log model, so that eventually, now that when we navigate to the experiments tab over here, I have in the model metadata, this is the runtime, this is the pipeline that I used, the model that I used, and other things that are useful. For example, this actually takes in a list of strings and will output a list of strings. And this is the model card. So as we mentioned before, it does go through the kind of biases and limitations of this model, how to get started, who produced this, and more information on the research paper if you're interested. So this is very good for logging purposes, especially if you work in a regulated industry. People are always talking about auditability and the need for better lineage over here. Okay. So now we move on to deployment. And deployment can mean many things, but really how large language models have changed model deployment is that we're talking about, firstly, multi-step inference graph. So it's not the case that we just call the model and get an output. Usually we will have to firstly convert the question into a vector representation, and then take the similarity between the question vector and the document vectors in our database index before giving the output of that to our large language model to get an answer. So there are multiple steps over here. So as we mentioned before, really what we want to do is to standardize on how we call the models and how we actually get back our results through a standardized interface. So you can see over here, whether or not we're using Chroma or OpenAI or Anthropic, we should be able to use the same code MLflow PyFunc to load the model and then call predict on our data frame. So the idea here is that we don't have to engineer specific inputs, inference code for each of the different APIs. We can just rely on the MLflow library to standardize everything for us. And another big question we usually hear from people who work in companies is also around cost and managing all these models. So if I want to use Hugging Face or if I want to use MPT30B, imagine if I have 3 developers and all of them put MPT30B onto a GPU for testing purposes. So MPT30B probably needs maybe 2 GPUs at least, 2 40 GB A100 GPUs, which are very costly. And if we do that across 3 developers, you can imagine that the cost is quite substantial. So ideally what we want to do is for an infrastructure admin to host one version of MPT30B and then allow different people within an organization or a team to then call this one model, so that instead of 3 different deployments, we're just working with one GPU. And the way we can do that is through an AI gateway, which again is a new feature inside MLflow 2.6. So the idea behind MLflow Gateway is to allow for better management of these AI models. Again, what we want is a standardized interface. So whatever model you can use, that's fine. But ideally, you have an admin team that has created a standardized API route around all of these models. And through these, you don't have to worry about leaking your credentials. You don't have to worry about exceeding your budget. The admin team themselves can set these limits and they can save the credentials inside the gateway server so that you as the end user, you just need to remember what the route is. And then you don't have to worry about credentials or what is behind the route. So this is an example of document summarization. Say if you're using OpenAI and you pass 20K models to it, and without 200K documents, and without any cost limiting mechanism, this will run overnight maybe, and then that will be very expensive. So ideally, you can set a quota of 5,000 documents a day so that you don't exceed your budget. So what this looks like in practice is if we have our chatbot over here. So what we want to do is say we've already indexed our vector search and we want to create an endpoint for a model. What we want to do is, here's an example where we call the MLflow gateway and we pass it the route name that we want to create. In this case, we want to use Llama version 2, and this is the 70B model. So we can create this route over here and include the API key so that finally when we want to call our gateway as an end user, I just do MLflow gateway query and I query the route name itself. And so then things like credentialing and what setting up this model on a GPU has all been taken care of for me. And as a data scientist, I can just focus on the actual prompt engineering and optimizing this model. So this is something that is definitely getting people are usually quite interested in because it's very easy to do a POC with an LLM you call OpenAI. But then what happens after that when you have 5 different teams who have large language model projects, you have multiple use cases, and when you put things into production also, you need to think about caching and rate limiting and all of those steps. So this is kind of like what happens next after the POC. This is usually a tool that people are quite interested in. So that is a tour of all the steps in our machine learning lifecycle. MLflow 2.6 is already here. You can just download it from pip. We have our AI gateway, the evaluation experience, updated inference parameters. The prompt engineering UI also is on its way. So if you're interested, this is the repository. There's a community Slack. We also have different LLM examples included on how to get started. And if you are interested in the demo notebooks for today, they're also on GitHub. You can run them in a Jupyter notebook or Colab. Don't have to use any specific platform. And I think at this moment, we are just right at 30 minutes, so we can open the floor for questions also.